Hello, everyone, and thank you really for being here today. I really appreciate it. So the official title of my thesis is called Hyperdimensional Computing for Biosignal Monitoring, Applications for Epilepsy Detection. But actually, now it doesn't work. But simplified version, I would call it From Brain to Brain, and I would explain why. So the motivation was to solve something that's a brain-related disease, so epilepsy, but the technique that we use is also brain-inspired. So we use hyperdimensional computing for the epilepsy. So why epilepsy? Epilepsy is a chronic neurological disorder that is actually having very unpredictable nature, and it causes people to have serious symptoms like they can freeze, they can start uncontrollably jerking, shaking, they can even lose consciousness, and even there is a potential to have SUDEP, which is sudden unexpected death in epilepsy. So all these imposes serious health risks and restrictions in their daily life. It is actually really significant portion of the human population that suffers from epilepsy. So if average human knows, let's say 200 people, probably 1 to 2 persons will suffer from the epilepsy. And despite all the technology that we have today, there is no actually widely available wearable device that would be able to detect all types of seizures. So how such system could look like? So EEG is the best signal that we have today to detect the epilepsy. And we would have to, for example, decide for a couple of positions where we would record, so a couple of channels, which then we could embed into the small wearable devices such as e-glasses or Epiphone that are currently being, for example, developed by other members of the lab. And then we would have a machine learning model that would run on such devices and hopefully be able to detect and even predict before the seizure happens. Since seizure change in time, since humans change in time and age, and also there are different environmental factors, it would be ideal if such systems could also be able to online retrain themselves and improve. And also in order for patients to be able to wear them and accept them, they would have to have a quite long battery lifetime, so for example, a couple of days, ideally. And so if we have several people like this, ideally we would want to have also a system where we could utilize information from these personal models to create general models, which would then have to be privacy preserving, of course, but also it would be interesting to use this general knowledge to later improve the personal models. So when looking long-term, ideally we would have such a decentralized systems out of outpatient monitoring, meaning out of the hospitals, and long-term, meaning a couple of days, weeks, even months and years. This could help us diagnose patients that actually have epilepsy and not some other neurological disease, provide alarms to the ones that have, and maybe even measure efficacy of different medications. Ultimately, hopefully it will lead to lower healthcare costs and help us designing personalized markers in medicine. But for us as researchers, it's also interesting because it could help us create long-term databases, but databases also that are more diverse in more real-life environments. So most of the databases we have today are only a couple of days and usually recorded in the hospitals, where in reality, the systems that we want to have is to work on when people are doing everyday activities, which introduce a lot of noise. So this could ultimately lead to better AI models. So real small crash course into the people who don't know anything about machine learning. So machine learning is currently being used for a wide range of problems. For example, for flower classification, if we wanna, this is a simple example, if we have 4 types of flowers, we wanna be able to recognize from the image what is the flower. We have usually a train set with about a lot of pictures of the flowers, and then we feed it into the machine learning model that then trains it in order to be able to, when given a test, really classify what was the flower, depending on different types of flowers, and then we can assess how good our model performs, what percentage of flowers it correctly classified. But in reality, usually most of the models require us to already extract certain features that will help them classify, meaning, for example, the color could be helpful to detect which type of flower it is, number of petals or shape, and so on. And this has been actually very much used in the healthcare domain, for example, for detecting arrhythmia from the ECG signals, for detecting stress from different wearable signals like pulse, breathing, temperature, for example, detecting cancer from the CT scans, or also in the epilepsy for detecting seizures from usually EEG, but also from other signals. So in this case, it looks like this. We have actually a signal that's, for example, EEG recordings in time from several channels. We discretize it. We look at different windows from which we extract features. So the windows are samples in time. And for each of them, we have usually label 0, for example, meaning no seizure, and 1 meaning seizure. And then we feed it into the model. And then we have a test, new data that we want to predict the label and assess how well this model performs. So, but unfortunately today, there is no good solutions yet for the epilepsy from several reasons. So epilepsy is highly complex disorder where here, for example, we see EEG patterns of one subject during 3 different seizures and on several channels. And we can see how variable the seizures and the patterns actually are. Second is that the patients and doctors also require extremely high sensitivity, meaning they want our system to detect almost 95, 98% of the seizures. At the same time, with almost no false alarms, so no false predictions that the person is having seizure when it's actually not having. And at the same time, the data sets itself are extremely imbalanced, meaning we have hours and hours of recording, and then we have only a couple of minutes of seizure, and then again, hours and days of recording. So in reality, even less than 0.5% of data is seizure. At the same time, the labeling process is extremely demanding, which can only be done by really experienced neurologists. And even they need to have a video usually to be sure that actually the seizure is happening and are not really ready to claim only from the EEG data. And many well-performing models so far are also very computationally memory complex, meaning that it's not easily to implement them on the wearable devices. So here comes the second part, which is brain-inspired machine learning, because brain kind of stores the information in a distributed manner. At the same time, it also performs processing of the information in a parallel way, and it is much more energy efficient than what we actually are with the current electronic devices. So here comes the hyperdimensional computing into a game, which actually is based on representing data in the form of hypervectors, meaning that whether we have a raw data, features, or image, all of this can be compressed and coded into one long vector. So usually it is binary vector, meaning that the values are 0 or 1, but they can also be other like normal numbers or floating points. And hyper meaning that it has a lot of numbers, so a lot of dimensions, usually more than 10,000. And this is interesting because it has several useful algebraic properties. For example, if we have 2 random vectors, the chance that they have the same number of the same position is very small, meaning that they are with basically what is called orthogonal. They're not similar. And at the same time, if we sum them up, then the result will be more similar to the ones that we summed up than to some other random vector. And this enables us quite simple approach to learning and then later also classification. So for example, several basic operations will be presented now. So if we want to say that certain feature has certain value, for example, that the color is pink, usually we have one vector that represents feature called color and one value, a vector representing the value pink. And then we, with the binary vectors, we XOR them. So we bitwise XOR every position. XOR means exclusive or it will be 1 only if one of the numbers is 1. And then if we have, for example, several samples that we encoded in such a way to get vector representing each sample, and they all represent the same class, we want to learn a vector that represents this class. And we do it by using the operation called bundling, or basically summing the vectors and majority voting. So if most of the numbers on certain position were 1, then it would be finally 1, otherwise 0. And then if we want to do actually the classification, so it means that we have trained, for example, 4 different classes. We have one vector representing each class, and then now we have a new sample that we need to classify. We simply compare how many positions have the same value, and the one class with the highest number of same values is the one that we give the prediction. So it's extremely simple way how it learns and classifies. So in reality, how does it work like? First, we have to initialize vectors that represent every information unit that we have. For example, for every type of feature, we have one vector. Same way, for every value that we want to map to a certain feature, we have to initialize. For example, if the feature was color, we will have for every color 1 vector. If it was a number of petals, we would have for every number vector, and so on. And then depending on whether the values that we are representing with vectors, if they don't have any relationship between them, then we can initialize them randomly. If there is certain order between them, like between numbers, we could initialize them, set these vectors so that similarity is more similar for the numbers that are closer to each other. And then we can also have even circular, for example. So in practice, this means that when we have EEG data, we have, for example, discretized it into windows of 4 seconds. And then for each window, we extract several features. And then we map together features with its value using the, for example, pink color and 5 petals with the operation XOR. And then we sum it all up and normalize to get one vector that basically represents that window. And then for using all the data, all the samples, we have labels and we have the vectors that we encoded. We sort them based on which one correspond to which class. And then finally, we end up with one vector for each class. So one vector that will be for seizure and one vector for non-seizure, for example, in this case. So to sum it all up, advantages of aided computing are actually quite broad, both from the software and hardware perspective. So the representing data in form of vectors is actually a distributed way of representing data, which makes it also redundant, meaning that if one bit flips, probably will still predict the same thing. And it makes it robust to noise, especially for low power devices, for small devices. Makes it also highly parallelizable, which can also make it even more energy efficient. The way how we can basically add another vector to the class, we can easily do the continuous online learning. So update the models as we are gathering more data. There's also ways to do semi-supervised or unsupervised learning even. And it is very interesting for distributed applications and privacy preserved learning. So from all of these reasons, it's actually quite interesting for implementations on the IoT and wearable devices. And that's why we started to test it for the epilepsy. But what was the problem? The problem was that it was not performing as well as we thought. And through the thesis, we kind of realized that there are 4 things that we had to kind of focus on to make it learn better or make it more interesting for the researchers to use it. And those are basically 4 chapters of my thesis. And for each of them, I will present only one small part of it. So first thing was that the data is actually spatiotemporal, which is quite complex. And then the question was how to map all this information between channels in time into the vector. Second was that the data sets, as I said, are extremely unbalanced. Third is that the nature of the epilepsy is quite personalized. And the third is that for biomedical applications, users usually require some interpretability. They want to know why the model is predicting what it is. So in the first chapter, there were actually more stuff that I worked on, but I will present only one. And this was on how to encode this spatiotemporal data. More specifically, so if we have EEG and we have several channels that are recorded in time, from each of the channels we extract features. Basically, we have 2D table. So we have a matrix. And if we have time, it would be even 3D table. And the question is how to then represent all this information into one vector. And here in this small part, I focused on encoding spatial information. So encoding the channels from which the information comes from. And does it bring improvement to the performance? So as I said, I initialized several different sets of vectors, one for features, one for channels, one for values. And then the question is how to then put it all together. So the simplest approach is what I call feature times value, because as I said, we kind of put together features and values for one channel, and then we repeat for all the other channels, but we never say which channel it comes from. And then the second approach was extension of this, but actually including the channel information. So here we see that before we sum it up, we add the channel kind of identification. Similarly, we can do it in the reverse order, that first we map channels, or we can do other combinations. And basically what I tested was whether when we measure the performance, so how well system that use specific type of encoding performs in the end, so how many seizures we will detect, we can see that the approaches that had channel information in the encoding approach, they all performed better. So basically, this led to the conclusion that it is actually quite helpful to include the channel information during their coding, even though it might be more complex for the encoding process, more operations requiring, but it still brings a significant improvement. Then the next topic was the unbalancedness of the data sets. And here I will discuss what I call multi-centroid learning. So as I said, the data is quite imbalanced. So two data sets that we use, one is CHB-MIT, which is scalp EEG, so non-invasive, and the other one is Sweat's ETHZ, which was intracranial EEG. And both of these data sets are publicly available. That's why we use them. They have more than 1,000 hours of recording. But when we look at how much seizure they had only 3 hours of seizure. So it means less than basically 0.4% of the seizure data. And so even if we find some feature that seems, for example, the amplitude often increases during the seizure, that seems to be good, that could separate whether seizure is happening or not. So let's say that during the seizure, the values are usually higher. So if we draw the histogram, if we take into account the amount of actually seizure data, it's completely engulfed into the non-seizure data. And this is why it makes it so hard to kind of classify without any false positives and with high sensitivity. So the question was, can we somehow learn better? So can we design some better learning approach rather than simply summing up everything together? And actually, what I proposed was actually inspired by the epilepsy. So let's say that we have data, we encode it into vectors. So every box is one sample that was encoded into a vector. And then ultimately, we learned what would previously be one prototype for seizure and one prototype for no seizure. But then because, as I said, seizures are quite personalized, the question was like, why would we restrict ourselves to have only one vector that represents all types of seizure? And at the same time, all the non-seizure data is when person can be sleeping, walking, talking, doing many different activities. So maybe it's too optimistic to be able to represent everything in form of one vector with 10,000 numbers. So we said, okay, let's allow more model vectors or more centroids for each of the class. And how does it work? Is that we have algorithm in 2 steps. So first, if we have a new data sample that, for example, belongs to the seizure, we compare it to the current prototypes. And if the prediction would be correct, so if it is more similar to the seizure, then we just update one of the seizure model vectors. But if it would lead to a wrong prediction, so if it's more similar to the wrong class, then we say, well, in this case, we need to add one more centroid for the correct class. But because this can lead to quite high number of centroids in the end, we had a second step of the algorithm where we were reducing the number of centroids. So either by clustering them, so comparing which ones are very similar and then merging them into one, or removing the centroids that were not very populated, so that were created maybe from only a couple of samples. And then how does it look like? So if we have subject 1, we can see on the top graph how many centroids. So we had 3 centroids for seizure, whereas almost 90% of the data was actually the most similar to the first one. And then for the non-seizure data, we had 15 centroids. And then for the other subjects, the situation is quite different. So there is quite large variability in the number of clusters per subject, number of clusters in seizure data or in seizures or non-seizure, and also how much data was basically the distribution of original samples that contributed to each of the centroids is quite different. So we have cases like subject 1 where almost all the data was actually in one, belonging to the one centroid, or subject 2 where there was actually quite almost evenly distributed. So then when we perform the second step, either removing or clustering them, we are removing in steps of 10% of clusters or clustering them in 10%. And measuring what's the performance if with this reduced number of clusters. And what we can see is there is nonlinear decrease, that even with reducing 50 or even 80% of the centroids, we can still keep the performance almost the same. So in the end, when we compare having only one cluster per class, so a regional approach, like hyperdimensional approach, with the multi-centroid, And then after 2 steps of removing, we can see that we have improvement for using the multiple clusters. And then if we have, we remove some, we don't lose performance. But ultimately, we wanted to test it on the more unbalanced data sets. So the first one was when we had balanced case where we randomly selected some non-seizure data so that it's the same amount of seizure and non-seizure. And then factor 10 means we had 10 times more non-seizure. And we can see that performance drops as the more unbalanced data set it is, but that multi-centroid approach can actually recover much more of the performance loss. And at the same time, if you look at the number of centroids, they can be quite high after the first step, but then after the second steps of clustering or removing them, they are increasing much slower as we are adding more and more data. So ultimately, we had in average 6 to 7 centroids per class. And this shows us that actually it is possible to design smarter learning approaches, and there is still a lot of space to improve it. Then the third topic was the personalized nature. So the idea was to first study how can we create general models from the personal ones. So if we have several subjects, each with its own seizure, the red one, or non-seizure model vector, and then we want to somehow put them together to be able to have generalized seizure and non-seizure model vectors. And then ultimately compare them with the personalized one. So the first thing what we did is we simply accumulated vectors of individual subjects to create general model. And then we compared how similar these general models are with every personal model, so every subject. And the idea was to see at what point the general models will not anymore change. So how many subjects we need to have a stable generalized models. And we see that for this RIPOMS data set that we use, it is in average after 40 subjects. And this was interesting from several perspectives. One is that this experiment cannot be so easily done with other machine learning models like random forest neural networks. It's much harder to compare the models and know what this means. And at the same time, it showed us that actually we need much more subjects than what most of the databases that we have today have. So most of the databases have around 10 to 20 subjects, whereas here it seems like we need 40 subjects to actually have stable general models. And then the question was, can we create some hybrid models? And can those models be useful in practice? So what would mean hybrid? So instead of having personal, which are good because they are usually more accurate, but they also require retraining for every new subject. So every subject would have to come to hospital, record several hours of the data so that we could have a model for the subject, or having general, which are better because we don't have to retrain them, but they're less accurate. So what we said, okay, but let's test what if we do combination of these ones. So what if we keep, for example, seizure from the general model and only personalize the non-seizure data, which is interesting because it means that we can only record when person doesn't have a seizure, which is much easier to acquire than waiting for person to actually have a seizure. Or on the other side, well, maybe we actually do need to personalize seizure parts because they are quite different between subjects. Which could also be interesting because then we don't need to retrain on hours of non-seizure data. We can retrain on only a couple of minutes from seizure data, which is much faster. So all of them are kind of interesting, but the question was like, okay, would they perform even good? So what we did is that we actually tested approach for transferring the knowledge between two different data sets. So the question was like, if one data set recorded in one setup in one hospital, and could these models be useful for another data set? And here we had 2 data sets. One was the RIPOMS data set, which was recorded here actually in Schuh, and it contains a lot of subjects, but it has only small amount of recordings. It had only seizure and 3 minutes of non-seizure before and after. Or we have this publicly available CHB-MIT data set that had only 24 subjects, but it had hours a week usually of recordings per subject. So what we did is we trained model on the CHB-MIT dataset and tested it on the RIPOMS. And so here's many things plotted, but what is interesting is that the dashed ones are the ones that were models from the different database, basically. And they were done in this hybrid manner. So we can see that what we try to achieve is something that can perform as well as personalized, so the blue ones. And we can see that the one on the top, on the right, the most right, is actually performing almost as good or even better. And those are models that had generalized non-seizure, and we only personalized seizure for individual subjects. And this kind of makes sense because, so it means that we could use the non-seizure model from the CHB MIT dataset, which had a lot of non-seizure data, which makes sense. But then the other way around, if we test models from REPOMS on the CHB MIT, the one that performs well is the one actually that has generalized seizures. So it means that we could use the model from the REPOMS only for the seizure, because REPOMS had actually more than 280 subjects, so meaning a lot of seizure data, much more than what we had in CHB MIT. So overall, the conclusion was that it is possible to use models from one data set to another, but actually we need a large and really long-term databases. And then finally, a little bit of interpretability. So I just wanted to show how hyperdimensional computing could be used for this. So the interpretability means, like, can we track in time what was the contribution of individual feature or channel to the prediction? And what we use here is one of the encoding approaches that I briefly mentioned before. And it is very simple approach. And it is called feature appending, where basically instead of putting everything together in a mesh, we kind of append them one after another. So I know that, for example, first 1,000 bits come from feature 1, second from feature 2, from feature 3, or the other way around, or the other features. So then we can basically use only some bits to check what would be the prediction if we only used first 1,000 bits or second 1,000 bits. And this allows us to see basically what would be the prediction if we only had one of the features. So on the y-axis, you see different features that we had. And then the red is when the seizure actually happens. And then you can see when some, for example, the gamma frequency had quiet, it wasn't very useful because it was almost always predicting non-seizure. And then similarly, we can do it if we are appending per channel, analysis of what happens with the channels, or which channels are what predicting and how. So, and we can see, for example, that some channels are much more prone to, for example, false alarms than some other ones. So this is interesting because it enables us a bit inspection of model working in time, understanding which features or channels are more useful than the others. And it is potential for building further understanding and improving the models itself. So finally, to conclude, so these are all the advantages of potentially using hyperdimensional computing for example, for epilepsy detection or other biomedical applications for wearable devices. But I focused in the thesis on these 3 topics only. So first, we analyzed how to take the raw data and encode it into the vectors in a way that it helps us and improves the performance. Second, we studied how to improve the models and the learning itself in the case when we have such an unbalanced data sets. Then we tried to create generalized models and then study the interplay between them and the personalized models to improve the performance even more, or make it more user-friendly and applicable for applications in the hospitals. And thirdly, we tried to see, okay, can we interest also the community by the potential for the interpretability? Of course, in future, there is so much more that can be done. So, for example, the whole question is like how to efficiently encode time information as well. We wanted to implement it also on the hardware to characterize performance and battery lifetime in reality, but it would need more time. Also, I believe that there is much more space to design better learning approaches. When talking about generalized models, for example, one idea that would be nice to see whether we can cluster patients into different groups of patients with this approach, and also extend and test this knowledge transfer on more data sets, not just 2. And finally, for the interpretability, as I said, the encoding approach I used is very simple, but I think there are much smarter and better ways to do it so that we can have even bigger combinations of different features. And finally, yeah, there were publications during this thesis for the conference and the journals, and I tried to make all the code available online. And that's all. Thank you.
we can share it here. Okay, so thank you very much, Una. As usual, everything fast. Okay, so let's do it well. I hope it was understandable. At least for me, it was, for the jury as well. So questions from the audience. Yes.
I was wondering, so I have never applied clustering algorithms as such either. The hard, as I understand, that sometimes there are problems because, like, essentially the distance from the cluster centers become evident. So can you comment on that? Like, did you ever have such a problem?
Well, here I measured the distance as like how. So the question was like for clustering algorithms, whether I had problems with that the distances were kind of infinite between the models, basically. Yeah, because of the high dimension. So in this case, the high dimension doesn't actually mean anything complex. It literally, so how I compare the vectors is you have, I don't know, 10,000 zeros and ones, and you use Hamming distance. I don't know, Hamming distance is literally on how many positions the values are different. So comparing, in this case, high dimensionality doesn't mean anything complex. It's just calculating Hamming distance between basically many combinations of different vectors and then kind of clustering them into the ones that are more similar.
Yeah. So I kind of understood that it was like you had 10,000 features, but it's not.
No, the features are actually all encoded so that you have one vector basically, and all the time you're operating just with these vectors of zeros and ones. Yeah.
One question.
Yeah.
So I'm curious, how, maybe I missed this, but how did we go from the ECG signal?
Yeah, ECG, EEG
To
vectors.
one.
Yeah. Okay, so it was not clear how I go from original EEG signal to vectors of zeros and ones. So there are many different ways to do it, but the most, let's say, broad one that kind of many other approaches can go under it is that you take a window and you extract several features. So you have to manually extract features like amplitude, frequency information, like what I had on one of these graphs, like line length, for example, or here were some features. We had mean amplitude, line length, bunch of frequency features, or some other features. Here I minimized the amount of them so that it would be like visible. But so you extract manually features, and then as I was showing, like you kind of map basically the feature with the value of the, so well, I don't know how to go easily back without the maybe I exit. Yeah, so here basically you extracted a bunch of features, so n features, and then the feature had value, which is actually one vector that you took from the table that you initialized here. And then you take also the vector that represents that feature, and then you kind of XOR it together. And then you do it for all the features, and then you sum it all up for all the features together. So this is the most simplest approach to kind of do it. Did I manage now? Is it clear? Okay.
But there are many others.
Yeah, there are other ways how you can do it. So
simplest one.
yeah, I don't know, Jonathan.
In standard machine learning frameworks, different approaches can have different range of feature. If I understand this framework, I think this gets lost, and given these are features, all features have the same weight.
Yeah, so I was actually, a question was that in standard machine learning models, often there is a way to assign certain weights to the features so that some features are more important than the others, and here it gets lost. Yes, it's kind of true. You kind of sum it all up together and they are all equally important. And from this reason, I do believe that there are better ways to design the learning. And I was actually testing one of them where the idea was that based on this appending, so knowing which bits comes from which feature, I can also know what each feature is predicting, but also know the confidence, for example, that this feature has. So, and then this helps me kind of sort. Basically, what I was doing is trying to design like feature selection that is embedded in the encoding itself, so that in certain moment, if some features are more confident, then I only can use, for example, them for prediction rather than all the features. And this can be done on a sample basis. So for every, like say, sample, I can see which features are more confident and, for example, use only them. So I was playing with this kind of ideas, and it did improve a bit. So there was one paper for feature selection, but in the end, my conclusion was that it didn't help significantly if it was done on a sample by sample basis. So it was still better to just do it once, run the feature selection, and then use only smaller set of features. But maybe there could be better ways to do it in time, and then it could be better, lead to better performance. Yeah. Yeah.
And I'm just wondering which of these chapters do you find most challenging and frustrating? Which one would you enjoy working on?
Okay, so I liked actually all of them, but for example, this interplay between personalized generalized is super interesting for me, because I think there's so much to like we would all want to have generalized models, but it's also maybe not realistic because seizures are really different. So maybe this kind of combinations between them can be helpful. And I still think there is a lot to explore, but most problem is that we really need a good data set. But the most challenging and annoying one was the last one, actually, because I had an idea how to do smarter encoding, where I have like fully connected layer of neural network that kind of does all the possible combinations of features, and I can still backtrace which feature was contributing to what. But then I just couldn't make it work. It was never better. So I really still hope to improve it and have a better way to do it rather than just appending them one next to each other.
Many scientists hope to see from EEG many things about the brain and mind. How specific do you believe this method is, epilepsy, and how much hope the method to be used also to figure out other things through EEG?
Oh, well, I think it's been applied to many different areas, not only biomedical signals, not only like EEGs. And actually, so when I started, the community of people using the hyperdimensional computing was relatively small, but there were a couple of people who were really trying to make it a community. So the problem was that at the beginning, there is actually a couple of terms for hyperdimensional computing. So the most common other name that's used is vector symbolic architectures. And I hadn't know about this term for like a year and a half after I started working on this. And the thing is that it's very hard then to find other people doing similar stuff. But then there are people who are trying to make it a community. They're organizing weekly events. And I became aware of that people are starting to use hyperdimensional computing and pushing it in many other directions, not just biomedical engineering. So, and we're all kind of struggling with the same problems of kind of convincing others that there are reasons to put work and research into hyperdimensional computing, other than just neural networks, whatever, deep learning. So yeah, I believe that there is a lot of interesting reasons to do hyperdimensional computing and apply it for different things, and many people are doing, but it's still a relatively small community when compared to other machine learning approaches and models. Pablo, okay.
So I was wondering, as far as I understand, like the mechanisms underlying the seizures are not really like entirely understood. So did you you showed this chart with all your channels, and some of them were like better at predicting and so on. So did you find anything that looks like some centers that could be like from which the seizures could be originating, like
Yeah, so the question was, since the origins of seizures are still, and the whole disease is still not completely understood, can from these graphs where I see like per channel, can I see somehow that, for example, the seizures are more centralized or not? So I was hoping to find it, but one problem was that actually in most of the data sets, we don't have labeled where the seizure comes from. So even if I see that, I don't know, two channels are close to each other, I could think, oh, maybe seizure came from there because, for example, they are the first one that started so there were subjects for which I did notice that some channels consistently started later saying that it's a seizure. But even then, I cannot know if this is just maybe a coincidence or actually the seizure was really there. Also for I think often it's not that clear. So when I was, I didn't put it here, but I was actually plotting this what Jonathan asked, like how, because I studied how features or channels are, for example, more confident. Then I could also, I plotted it in a spatial graph of the head. So I could see which positions on the head are more contributing to the, for example, correct predictions. And what was interesting is based on these graphs, it was not always like clearly, like centralized. Often it was that there were some channels that are, let's say, next to each other, but then some other channel was completely on the other side of the head, was actually contributing, what was very good for classification. So it doesn't mean, of course, that approach was not really detecting the localizing the seizures. It was more detecting the channels that are useful for classification, whether it's because the seizure was below them or because of some other reason, I don't know. But so for a moment, and I couldn't confirm why some channels are, because I don't have really labels where the seizure comes from. So that is hope with the better and new data sets that we could also study these things.
Very clear, the doctors don't really know where the seizures come from, so it's very difficult to validate any assumptions.
Yeah. Christoph? Thanks. So the question was whether this could be, and whether I thought of using it to not just EEG, but more signals like EEG, ECG, respiration, temperature, whatever, and basically do the sensor fusion for this. So I did actually, and I had a student where idea was to kind of have multiple sensors, multiple modalities, and then also kind of visualize in this way which modalities are kind of confident or not confident and which moment into the prediction. But the problem was that the data sets that contain multiple modalities are even less available. So we had in the SHUV, they were in hospital in Lyon, we recorded one data set, and they're actually recording it still. But when we started digging into data set, we spent 3 months cleaning the data and trying to be sure that that we have correct labels, like synchronizing everything. So in the end, we never got to the part of actually training it on this. So it would be also nice to do it. Yeah. Maybe
It's part of the future work, by the way.
Yeah.
It's mentioned there because other people were trying to do it, but actually doctors consider EEG as a standard clinical procedure for epilepsy, so they don't typically do it. Do you have more people?
Yeah, there are a few questions here.
Okay.
Okay, just a few more questions. Did you also test whether you can use this approach to predict seizures before they happen, and how, yes, if yes, how much time before the actual seizure occurs? So I didn't use it to test the prediction, because prediction is much more challenging than the detection. And currently, there is in general, not a lot of work on prediction. And even if there is, it's still bit discussable how to even do it. So what has been the most promising so far is that the models would say in the next couple of hours you have higher chance that you will have a seizure, but not really in the next 3 minutes you will have the seizure, even though people were testing, basically classifying classifying between 10 minutes before seizure and 3 minutes before seizure, but it's extremely complex. So if I had time, I would have done it, but I am not very hopeful that this would really work so well. And then the second question was, how does AG computing approach compare to state-of-the-art models on data sets used in diseases? Okay, so this is the whole question, and this was actually chapter 1 of my thesis that I didn't mention here. Because when I started working on this, I was annoyed how hard it is to compare to state of the art, because every paper had different data set, different data preparation or pre-processing, different cross-validation, train test split. Half of the things were never mentioned. So it was basically pointless to compare any numbers, because I didn't know what these numbers mean and how to even replicate them. So what I did is that I only decided to use random forests as basically a golden standard that's performing relatively well. It's relatively simple to implement. But then I implemented it, and everything was the same, whether when I called the model was the HD model or random forest. And this was for me something that was like a bar that I was trying to reach. And in these graphs, usually whenever I was, where's the mouse? Whenever I was plotting or comparing the performances, I usually always had the random forest as a reference. So for example, here, these gray ones that basically you don't see, or here you see, this is the random forest. So this is what I was trying always to kind of achieve and be better than that if possible. Ideally, yeah, I would like to compare it to all other models, but it was a lot of, even now we are discussing which models we would even want to compare to, because there is so many things proposed in the literature. And okay. And were there any tries of encoding the time component as feature? If yes, what were results? In talking about the time, we actually tried one approach where we were designing a new feature that was kind of including time information into it. And these features were, I didn't present them here, but these features, because it's actually going to be presented probably by Renato in a couple of months, because he worked a big part on it. So, and this was, yeah, we designed features that include time information into the features itself. What I wanted to try was also in this kind of way of when do I map and how do I map things into the one vector, whether I could do some smart way to include time, but I also didn't have time to try that, but that would be the idea also to try. Okay, I think we're done with the questions online.
Any other questions here? So we are finishing this part.